Got it. Okay, so we are recording. So if you look in the chat to this, I sent this the session 2 wiki page, which is what we're going to use to download our materials and files for today to get started. So let me turn my video off and share my screen. Screen number 2 is what I want. Yes. Okay, so right now I'm displaying my screen, which is the session 2 wiki page. And again, there's a link for that in the chat. So what you'll see right down here, as I mentioned, under prerequisites, you'll see session2.zip. If we click on that, it'll probably give you some kind of box like this. Go ahead and click download. I've already downloaded this file, so I'm not going to download a second copy of it, but it'll appear in your downloads folder on the machine. So for me, since I've already downloaded this, I'll just skip right to my download. And you'll see it as a zip file. So you'll have to unzip that file. Typically that'll work just by double clicking it. I imagine Windows is similar. So you'll get a folder that looks like this. It'll say Data Analysis 2020 Master Session 2. So that is the file. That's the data that we're going to use today. So the first step, if you remember from last time, is to start up Anaconda. So Anaconda Navigator, so that's the app I'm going to open. That's what we're going to use for this. So if you go to your programs and fire up Anaconda Navigator, you'll see it'll start to load. Okay, it wants me to update the application. I'll say remind me later. I don't want to do that right now. So this will probably take a minute. And you'll see hopefully a familiar screen that looks something like this. And so just like last time, we're going to want to launch a Jupyter notebook. So we'll go over here to the cell that says Jupyter notebook. We'll click launch. And so that should open up a new tab in your browser. And that tab, just like last time, is going to be on a Mac. It would be similar to your Finder. On Windows, how you navigate through your directories. And so for me, so we're going to want to now navigate to that file we just downloaded from the wiki page. So for me, that's in downloads. And we'll go to last modified, which is here, session 2. And now you'll see we're in the correct area for session 2. So you'll see this first file, session2.ipynb. That file extension stands for IPython notebook. So that's the Jupyter notebook that we're going to use today. And you'll see a CSV file here, A220 take rate data CSV. That's some of the data we're going to load in today. So we're going to fire up our notebook by clicking on session2.ipynb. So we've opened up our notebook, and we'll wait a minute for the kernel to get ready and load. And we'll see a screen that looks like this. So session 2 modeling basics. So if you remember from last time, we got at least at a cursory level, familiar with how to load data with pandas in these notebooks, make simple plots, stuff like that. So we're going to build on that a little bit today. And before we start on that, I want to address some questions. I got a lot of the same questions at the end of last session, which was how can I connect my notebook directly to Redshift data? So I want to be, how can I write a query directly in my notebook and load that immediately into a Pandas data frame? And the way you'll do that is with this cell below. We're not going to execute this today because I'd have to give you my name and password to do so, but I'll show you exactly how to do it. So with your Anaconda distribution, there's a package called SQL Alchemy, which is really great for connecting to Redshift. So we grab we import some stuff from SQL Alchemy. We import pandas, an alias that is PD, and then we import this time. I'm importing the time module in Python so we can see how long it takes to run our query. So right here, we're going to specify our Redshift username and password. For me, that's just, I think it's C Mueller password. I'm obviously not going to type that here, but you guys get the idea. For the connection string, this will remain unchanged, and it's formatted with our username and password. Then we create this engine object, which is an object, a SQL Alchemy object that we're going to use in a moment, and you can read more about that by looking up SQL Alchemy and just how that works. And here is our query. So my query text is a string wrapped in triple double quotes, as you see here. I highly recommend this for any SQL queries that you're going to write. But it's formatted just as a string in Python. So for this example, it's going to be a really simple, okay, select star from XDW dim flight limit 100, a nice, easy, manageable query to use for this example. Then we're going to go ahead and go down to here, and we're going to say PD, so that's pandas, read SQL query, which is a pandas function, and then we're going to pass it our query and the engine that we define, the SQL Alchemy engine that we defined up above. And so the time module comes in to play here when we actually execute the cell, and we can see how long it took, just how long it took to run that query. And then at this point, once it's run successfully, we have the results. Data frame, and we can, do whatever we want with that data frame. In this case, I've chosen it to save to a CSV file, which we are familiar with. So I encourage you to experiment with this on your own. Please ping me if you have any questions, but we're not going to run this today. We'll save this for later on our own time. So let's pivot now to the actual modeling portion, or the predictive analytics portion of this of this course. So when I say predictive analytics, in this case, I'm talking about machine learning. And so machine learning, you probably hear it all over the place, and I think a lot of people have a really good understanding, probably better than me, of what it is. But I think it might be kind of a new term to a lot of folks too. So I'm going to take a little bit of time and describe what we mean when we're talking about machine learning. So the first thing to kind of address is there's two flavors, we could say, or two categories of machine learning. There's supervised learning and unsupervised learning. So first, I'm going to cover supervised learning, and that's pretty much all we'll deal with today. And then I'll describe unsupervised learning and how that can be useful. So, okay, so let's dive into supervised learning. So there's two types, well, really three, but we're mostly going to focus on the biggest two types of supervised learning, which is classification and regression. I imagine the bulk of you are very familiar with this, how to distinguish between these two. But for anybody that's not, the way we can define what a classification problem is where we're trying to predict a discrete class label. So you can imagine we have some data, and we're trying to predict a classification in our data. And there's two labels that we have. And for this example, we could say we just have label A and label B. So we give some data to a model, and we say, okay, model, I've given you this data. I want for each example an output, where the output is either A or B. That's a classification problem. So we're classifying our examples as either A or B. To give you a kind of a concrete example of this, you can imagine you have pictures of just dogs and cats, and you want to be able to feed those to a model and have the model immediately tell you for each picture whether it thinks it's a dog or whether it thinks it's a cat. There's a lot more examples of this. The examples I've given are binary classification, but there's multi-class, where you don't just have two classes, you have n classes, and we'll cover that and address that a little bit later. But right now, I think we've covered that enough. So now I'll talk about regression. And regression is a little bit different. We're still predicting something, but what we're predicting in this case is not a class label, not a discrete class label, rather a continuous quantity. So a great example for this is predicting home price. So you can imagine, you have some input data. You've got maybe zip code, maybe you've got square footage, taxes, the price that the closest home sold for most recently, stuff like that. So you can imagine feeding all that stuff in and into a model and having that model produce home price, which is a continuous quantity. Obviously, it can go anywhere from 0 to I think probably the sky's the limit. So that's a really great example that I like. What we're going to work with today is trying to predict take rate for a flight, given route, duration, fleet type, et cetera, stuff like that. And just one final example, one thing I've worked on more recently is trying to predict the NPS score for a single flight, given things like availability, upload, download speed, RTT times, stuff like that. So regression, the key thing to remember is we're predicting a continuous quantity. Now, there's a third kind of flavor of supervised learning, which is called anomaly detection. That's kind of a world of its own. So I won't touch on that too much today. So let's pivot now and talk about unsupervised learning. So unsupervised learning can best be described as, and I thank my colleague Mika for lending me this quote here, but it can be, let's see. It allows us to approach problems with little or no idea what our results should look like. Basically, we're trying to derive structure from data where we don't necessarily know what we're looking for. We're just trying to uncover like patterns, and we don't necessarily know what we want out or what we want to do with the data. That's when unsupervised learning or clustering can become very useful. And so we'll cover that a bit later. So first, let's focus on supervised learning, where we're telling the model what we want. And the best example, I think, is to consider the equation for a line, which I think a lot of people are familiar with from middle school, which is just y equals mx plus b. We're all pretty familiar with that. Yeah, x is a variable, y is a variable, m is the slope, b is the y-intercept. You get the idea. So the relationship can be described, that relationship can be described as some function of x, or f of x. So f of x, of course, is always equal to y, and that function looks like mx plus b. So the relationship in that data is described by this function f of x. So this is great. And so, maybe you're probably thinking, why are you talking about the equation of a line? And it actually ties in really well with, it's a great analogy for machine learning. So for every example that follows, we're going to use this sort of paradigm where we have some x, some input data, and we want some output data from our model. Basically, we want a prediction. So y is going to be our prediction, and x is always going to be the data we're giving in. So you can imagine, you feed in x to your function, and you get out some value y. So that's kind of the same concept in building a model, a machine learning model. So to use the home analogy, x is going to be in just a single variable example. We're trying to predict home price. So y is going to be home price, and x, we're just going to, like I said, consider a single variable, and x will be square footage. So life is good when we can describe our data with a really simple relationship like that. But I think, as anybody probably who owns a house or is contemplating owning a house knows, the relationship between square footage and home price absolutely cannot be described by a simple equation like this. It's far more complicated. So this is a good illustration of why machine learning can be useful. And so it turns out that most problems that we encounter, you can't just describe the function with a simple equation like we wrote above. But it's really useful to think of the relationship as a function, f of x. So there is, of course, some function that describes the price of a home given some inputs. It's just not a simple equation we can write down in a single line. So, okay, this is where machine learning comes in. So without a mathematical expression, we'll never, be able to exactly predict y given x, but we can get really, really close. And in a lot of cases, very close enough to solve our problems. And so what machine learning is trying to do is use a model or algorithm to learn that function f of x, which we don't exactly know, but we have an idea of, and the machine learning model is learning that function, which describes the relationship in our data. And so how well our machine learning model can learn that function f of x directly translates to how well we can predict y. So our goal here is to train a machine learning model, which we're going to represent with f prime of x, such that our machine learning model is really, really close to the actual relationship in our data. And so that's really the goal here. And as we saw before, f of x is just equal to y, the thing we're trying to predict. So the closer we can get f prime of x to be f of x, the better predictions we're going to have. So that's the idea. So to do this, in these examples, we're going to use a Python package called Scikit-learn. Scikit is a awesome package, especially for just starting out, as well as more advanced stuff too. So I definitely recommend giving a look to the Scikit-learn package, and I've got a little link here if you want to read more about it. So that's what we're going to use. So let's import some things that we're going to need. I haven't imported any Scikit stuff just now, but we're going to import some system stuff, some plotting tools, Pandas, a random function. Don't worry too much about that. And we're going to go on now to our first, what I'm going to call a toy example. So in our toy example, we know f of x pretty much exactly, but we're going to try and train a model to see how close we can get that model to learn our function. So that's what this cell is doing under first example. So we're going to generate some data based on a function we know really well. So we're going to create a data frame, we're going to create some x values, and we're going to create some y values. So we'll run this cell, and we're going to print some info about the data we just created. So the data is called my data. That's a Pandas data frame. It's got 200 rows. 200 data point, examples basically, and of course we've got x, which is going to be our input, and y, which is the output that we're trying to get. So that's what our data looks like in the data frame. So let's plot our data, which I always recommend before doing any modeling exercise. So we're going to use the matplotlib scatter plot function. So we'll plot y as a function of x here. We'll label the axes. So you can see that, okay, there's a pretty linear relationship here, but it's not exact because you can see there's some scatter and jitter and noise in these points. So that's what our data looks like. Okay, so one of the first steps in machine learning is to split up our data in terms of training and test. And so we're going to use a function for that. And now I think it would be a good time to talk about, what kind of model are we gonna use? And this is a really deep kind of philosophical question. But you can see from here that the relationship's very linear. So we probably want to start with some kind of linear model. So from scikit-learn, we're going to import linear regression. That's the model we're going to use today for this. And we're going to import some other things too, this train test split function, and we're going to import NumPy as well. So as I mentioned, the train test split is kind of the first step in any machine learning workflow or pipeline. And the idea is that you divide your data. In our case, our data is 200 rows. We're going to divide that data into a training data set and a test data set. And the idea, or maybe a good analogy to think of, is the training data set is like if our model was taking a college class or something. The training data is like the homework and the lectures, and the testing data is like the test. And so the model is really doing its learning from the training data, and we're evaluating how well the model learned on the test. So we're going to do that with this function, and it's going to give us our x training, our x for testing, our y for training, our y for testing, and this is our model that we imported, or our function, scikit-learn function that we imported above. So we pass it x, we pass it y, we specify this thing called the test size. So this is the fraction of our data set that we want allocated to testing. So here I set it to 0.2 or 20%. So that means 20% of our 200 rows are going to be set aside just for testing, and the remaining 80% is going to be used for training. So what value you pick here really depends on the problem that you're dealing with, the model that you're using, how much data you have, stuff like that. 20 to 30% is, I'll just say, a good place to start. And then here I specify this thing called random state. So the way this works is it randomly splits up data So it doesn't do it just in the order that you receive it. It randomly splits it up, and by specifying the random state seed, which we've done here, you'll get reproducible results in terms of your train test split, which is really important for evaluating how your model's doing later. So I definitely recommend setting this random state to something if you need reproducible results, which is pretty often, I find, in most cases. Okay, so to feed our data to our linear regression model, we have to do a little bit of data, we'll call it being like data cleaning. And so these objects, as they're returned from our function, are actually Pandas series. And so in this case, our model expects one-dimensional arrays. And so that's all we're doing here. We're converting our training data, xtrain, which is a Pandas series, to a one-dimensional array. And again, that's what we're doing with y as well. So that's what we're doing with these two lines. So let me run a couple of these cells now. Make sure I ran everything here. We'll run our train test split. So that's done. We're going to load our model. So we're going to set f prime, which is our model, equal to linear regression. So that instantiates our model object, which is f prime. And then we're going to train the model. And in Scikit-learn, all of the models are going to be trained with this function called fit. And so when you call fit, you almost universally in any scikit-learn model you deal with, fit is running the training of the model. So we're fitting it on external, which is our training data. So we'll go ahead and run this cell. Okay, so we've trained our first model. So okay, the training or learning is done, and now it's time to measure how well our model did at learning the data. So this is a key step, another key step. And what we're trying to do when I say measuring model performance is answer the question, how much did the model learn in training? Kind of like what any kind of test in college is asking. So, you know, to formulate this, what we're really asking is how close is f prime of x, our model, to f of x, the real function that describes our data. So there's a lot of different approaches we can use to answer this question, and which approach or metric we use depends on the data and the problem and the model itself. For this example, a really good starting point is called the mean squared error, or MSE, and so the best way to describe that is, you know, we've got f of x, our function that actually describes our data. We don't necessarily know it so well, but we know that if you put in x to f of x, you get out y. And we know that our model, f prime of x, is going to give us a prediction of y, which is y prime. So the mean square error is calculated as the average of the difference between the prediction and the actual value squared. So the lower that MSE, the better your model is doing, because the closer your predicted value, y prime, is to your actual value. So of course, scikit-learn has a really great function for this mean squared error, and I've got a link right here. But there's a lot of other, what you could call this a cost function or a loss function. There's lots of other options available too. Check those out as you're curious and have time. But for now, we're going to stick with mean squared error. So we'll import it right here. We're going to define our y prime, which is our prediction. We get a predict from any scikit-learn model by calling the predict method of our model object. So we're predicting our testing data, and again, we're reshaping it to a one-dimensional NumPy array, which is what this particular model, that's how it needs to receive the data. So y prime is our array of predictions from our model that we just trained, and y is the actual values. So we're really comparing, you know, how different is y from y prime on average. So we'll calculate my MSE by loading in our scikit-learn function, mean squared error, and then we'll print that MSE out. So we'll go ahead and run that. So our mean squared error is 40. Okay, so that's that's our quantitative measure of how well did we do here. So you can imagine kind of tweaking things in our model and then comparing, you know, what do we get out for our mean squared error? And we can, you know, the lower we can get MSE, the better off we're going to do. So let's plot our data. Let's plot our predictions, our test actual values versus our predictions from our model. And we'll do that with this matplotlib cell. So I'll hold Shift and push Enter. So we're going to label our testing, our actual values as actual, which is the red crosses in the plot down here, and the predictions from the model that we just trained as the blue dots. So you can see, and again, this is just our testing data. You can see that given some x, oftentimes the blue dot is awfully close to the red cross. So our predicted value is most often really close to our actual value for a given x. And so the mean squared error then is just taking the difference between blue and red, squaring it, and then taking the average of that for all these data points. That's what mean squared error is. So the smaller the better is the conclusion there. So okay, we've done this now with some test data to kind of warm up our intuition of how this stuff works. But let's use some go-go data to see how we can solve a real problem. Before, I hope I've illustrated that, given some inputs, which we're denoting as x, we can predict something. And what we're trying to predict is y by fitting, by fitting a machine learning model. So if you imagine we have a bunch of A220 flights, and we want to be able to predict the customer take rate on those flights. And you can imagine why this would be really useful. So, in the paradigm we've got, y is going to be the thing we're trying to predict, which is take rate on a particular flight, and x is going to some data that we're going to use to make that prediction. So it's going to keep things really simple, and we're just going to use the flight's duration. So we're trying to predict take rate based only on flight duration. So that's the goal here. So let's load in our data with Pandas. So we're going to call our data frame A220 data, and we're going to call Pandas read CSV, and we're going to read our CSV file, and then we're going to print some info on it. So this came with your download. I've already prepared this data. And so what you'll see is, okay, we've got almost 10,000 rows. So that is, each row is a flight. We've got we've got about 6 columns. So we've got flight ID. We've got the hour of the departure date time, which is an integer. We've got the month of departure date time, which is a string. We've got the total service duration, which is an integer. We've got the weekday, and weekday is like Monday, Tuesday, Wednesday, you get the idea, as a string. And we've got take rate, the thing we're trying to predict, as a string. So that's a little weird. We would have hoped that take rate is a number, since that's what we're working with here. So let's do one thing first, and I want to rename all these columns to have lowercase and no spaces, just to keep things nice, consistent, and stick to a coding standard. So we'll rename the columns with this function. We just pass it in a dictionary with the in place equals true. So we've changed our column names to be a little bit more workable, and we'll take a look at that data frame down here. So you can see this is what our data frame looks like. So we've got, as I mentioned, flight ID, which is a string, departure hour, integer. You get the idea. And then we've got take rate, which is a string. So because this is a string, the first thing we want to do is convert it to a number. Before we convert it to a number, we're going to want to remove this percent sign. So we're going to do that with this line in the cell down here. So we're going to redefine our take rate column as it's still going to be a string, but we're going to replace that percent sign with an empty string. So that's the first step. Then the next step, after we've removed that percent sign, is we're going to convert that string to a float using this as type float function. And then we're going to print the info to be sure that we did this correctly. So let's hit Shift and Enter and run the cell. And what we see down here is that take rate is now a floating point number. So that's great. And if we want to take another look at our data frame, we can just print that again, and you can see, okay, great. We've got this, the percent sign's gone, just as we expected. So this is a nice number now from 0 to 100 that we can work with. So you might be wondering, okay, this is a course about machine learning and predictive analytics. Why would you go through this example of how to like clean some data? And the reason I do this, and I think it's really important actually, is that the majority of your time when you start to tackle these problems is going to be spent preparing the data and getting the data into a format that your models can understand. I would say that's like at least 3/4 of the time and effort is getting the data prepared just to feed to the model. And so I wanted to introduce a little bit of that here. So when you tackle these problems on your own, hopefully you won't be discouraged at how much time you really have to pour into data preparation. I just want to know, and I want everybody to know and share that this is a really important part of the job, actually, and actually what takes the most time. Okay, enough on that. Let's make a plot of our data just to see. So we're trying to predict take rate on A220 flights given the flight duration. So let's plot those two things, and we're going to plot them just like this using matplotlib. And you can see, okay, I labeled these as X and Y, not very useful. X is the flight duration in minutes, and Y is the take rate. So you can see what our data looks like here. Obviously, it's a lot messier than what we saw in the example above, but you can see as the flight duration increases, the take rate goes up, which I think is, kind of consistent with our intuition about this. I don't think this is going to be too surprising to anybody. Great. All right. So let's now do our first linear model where we run these predictions. So we're going to do our train test split just like we did before with our data. So we're giving it our flight duration, our take rate, and we're getting our train test, train and test stuff. So this is, we've gone through all this before. So we're reshaping those Pandas series to be dimensional NumPy arrays. We're loading our model, we're training our model, and then we're running the predictions on the test set, and then we're calculating the model performance using mean squared error again. So let's hold that. Let's run this cell. So we'll hold Shift and push Enter. Okay. So what we see here is we've got a mean squared error of 105.2. So this is what we'll call our benchmark. So the goal now is to try and beat this 105.2, basically train another model and get a mean squared error of smaller than this 105.2. So how can we do that? Well, there's a couple of things we can do. When we look back to our data set, we have a lot more than just flight duration, which could be useful in predicting take rate. And there's other more sophisticated models we could use too. But first, let's just see if we can give our data some extra information about how to predict stuff. So you can see another nice kind of natural choice would be the departure hour. Obviously, flights during the middle of the day, I would think, are going to have a higher take rate than flights, red eye sort of flights. But let's see, and the way we can inspect some of that data is by giving a data. We're going to use this Seaborn pair plot function, which is a really cool function for visualizing data. And what we're going to want to see is flight duration, departure hour, and take rate. And we're going to specify this diag as hist. I'll show you a little more about what's going on just by executing this cell. Okay. So what you should see is a cool visualization of our data set. And so what you see is our data, we've got take rate, the thing we're trying to predict, departure hour, one of the inputs we're going to use, and flight duration, another one of the inputs we're going to use. And you can see it's a matrix, and the diagonals of the matrix are just flight duration and flight duration, departure hour. So those diagonals are just histograms of our data, and the two-dimensional scatter plots are just scatter plots of the labels on the axis. So if we pick this plot right here, we've got departure hour as a function of flight duration. Here we've got, in this lower left-hand corner, we've got take rate as a function of flight duration, which looks like what we saw before. So what we're trying to do with this is use departure hour right here and see, does departure hour really depend, or does take rate really depend on departure hour? And if we look at this 2D scatter plot, you can see okay, well, there's kind of a weird relationship here. It's not quite linear, but there's definitely something going on. So okay, there's definitely some structure here. Let's see if we can kind of exploit this a little bit. So now we're going to use two features. So if you notice, I just used this this new term called features. So a feature in machine learning is basically the input to your model. In our case, it's going to be X. So whatever your X is, those are referred to as features or input features to your model. So before we used a single input feature, which was flight duration. Now we're going to use two features as input, which is flight duration and departure hour. So now we're giving the model a chance to learn a little bit more data or learn a little bit more information, hopefully, by using departure hour in addition to flight duration. And again, we're just trying to predict take rate here. So we'll run the train test split function just as we did before. And we'll get our data split up into training and test sets. Let's fit our model now again, but remember the key thing to realize here is that our X is now two columns as opposed to one. So we're feeding our model not only flight duration, but we're also feeding it departure hour. And then we're going to predict our test set, and then we're going to calculate the mean squared error. So the key question to ask here is how far off are the predicted values from the actual values? And that's, again, judged by our mean squared error. And as you can see right here, our MSE is 103.8. And if we compare that to up here, 105, so we've beat it. We've beat it a little bit. So there is some information that our model is using to do a better job at predicted. So there is some information that the model can use buried in departure hour to better predict take rate. But so far, we've just used a linear model. And a linear model is really kind of the simplest machine learning model that we can use. There's a lot more advanced models out there, and one of the models that we can, one of maybe more advanced models we can use is a support vector machine, or SVM. And so we're going to play around with an SVM now. It's quite a bit more sophisticated than a linear model. And so unfortunately, I have to say that support vector machines, that is a whole class or set of classes, or maybe even a course unto itself. So I'm not going to go into like really deep detail about how support vector machines are really doing their thing, but just know that it's a solid model to use for this purpose. There's tons of outstanding explanations online. There's a great YouTube video that I link right here, but we're going to use an SVM. And the key thing to remember about the SVM, or just any model in general, is we've still got this F prime. And we're still fitting it, and we're still predicting stuff. So whether it's a linear model, whether it's an SVM, whether it's a neural network, let's just forget about what the model actually is right now. We can think of it as a black box that we feed input features to X, and we get a prediction, a Y prime out of. So I strongly encourage you to read up on how the SVM really works. And maybe the next thing I can say is, why are we picking an SVM out of dozens and dozens of great models out there? And the answer was actually kind of guided by a link that I had opened up earlier. Let me go up here for a second. It's this chart, this link right here under. So if I click this, it's going to open up a new tab. And it's a really useful chart called Choosing the Right Estimator. So we'll follow this flow chart here. So it's kind of a cheat sheet. So, okay, we're at the start. So do we have greater than 50 samples? Well, we know from our data that we just looked at, the A220 data, we know that we have 9,671 samples. So yes, we have more than 50 samples. Are we predicting a category? No, we're predicting a continuous quantity. So we'll go no. We're predicting a quantity, yes. Do we have less than 100,000 samples? Yes, we do. So we'll go here. Few features should be important. The best way I can answer this is I don't know. So, we really have a number of options we could try here. We could try a lasso model. We could try an elastic net model. We could try a ridge regression model, Or we could try a SVR, or support vector regression, which is just, there's two kinds of support vector machines: support vector classification and support vector regression. So SVR is what I decided to pick. So that's what we're going to go with. And so what I'll say about this page is it's really great, but it does not do enough justice to how many great models are really out there. There's tons and tons of models that you won't see in this flowchart, but are super useful at solving problems. So I would suggest this flowchart as a way to guide you to thinking about how to use different models for what problems, but it's by no means a complete or exhaustive list. So yeah, I'll stick with that statement and move on. So that's kind of how we settled on a support vector machine. So I covered some of that, and so I introduced this new buzzword called hyperparameters. So what are these hyperparameters? So I like to think of hyperparameters as like knobs or dials on our model that control different aspects of how the model learns during the training, and they have to be set before the training ever begins. And so picking the right settings for these hyperparameters is extremely important to in this learning task. So different models have different hyperparameters, and they control different things. And knowing the correct settings of these hyperparameters is a little bit intuitive, which is partly based on experience and partly based on kind of understanding how the model works. So that's pretty essential to know how to do that. But it is, largely trial and error. So a very empirical, iterative process, and it depends very strongly on the, your specific example that you're using to. So. There's this crucial step that we have to machine learning workflow called hyperparameter optimization, or hyperparameter tuning. I'll provide a good link here. So the support vector machine has a number of these knobs or dials, a number of these hyperparameters. So if you click on that link, it'll link you to an explanation of what those hyperparameters are really controlling. But just know that we've got these little settings that we can tweak and get different performance. And we don't necessarily know off the bat which one's going to be best. Okay, so we're going to import our support vector machine, SVR, support vector regression, from Scikit-learn, and we're going to set our model f prime equals SVR, and we're going to set this thing, again, this is a hyperparameter called the kernel. We're going to set that kernel with this, the setting we're going to pick is RBF, or radial basis function, and again, you can learn more about that later. And then we're going to train the model by fitting it on our training and test data that we defined above, and then we're going to predict, and then we're going to calculate the MSE. So let's go ahead and run this cell, holding Shift and pushing Enter. So it's training, and what do we see for our MSE? Well, we see that we get 101 basically 102. But that 101.97 is less than what we had up here. So the support vector machine is doing a better job than our linear regression. So we are improving. We are getting better. So to see what hyperparams are available in any model, we can call the getParams method of our model object. We can see there's a lot of them. There's this C parameter. Actually, it's very important what this is set to. We've got our cache size, coef 0, degree, epsilon, gamma, kernel, max iteration, shrinking, tolerance, verbose, just how verbose do you want the model to print stuff out during the training. A lot of different settings. We don't have time to go through what each of these is controlling, but in the links above, you can are more than adequate to understand what all of these things are controlling. So this is a great time now to pivot and talk about this grid search and cross-validation. And so there's a question, kind of a rhetorical question, is wouldn't it be great if we could just tune our hyperparameters automatically? And of course, there's a function for that called grid search CV. And basically what it does is it trains the model a bunch of times for each setting of hyperparameters that you want to specify. So you can imagine your setting of hyperparameters is kind of like a grid. And so it just scans through that grid of different hyperparameter values and picks the best, the one that happened to perform the best. And the way it chooses which one performed the best is really important, and that's done with a technique called cross-validation. And so cross-validation is a extremely important step in our machine learning workflow. I would call it maybe a best practice when training any model. And basically what cross-validation does is it splits your data into your training data into some number of subsets. In the example we have here, we're going to say it splits it into K subsets, where K is 1, 2, 3, 5, 7, 10, whatever. Usually K has a value like 3, 5, 10, something like that. But there's no one correct answer. So once it's split your training data into these K subsets, or what we often refer to as folds, the model is trained once on each of the K subsets, and it keeps the last subset of those for validation. So in this visualization down here, in our training data, you can see we split it up into these 5 subsets. And basically, the model is trained the model is trained on 4 of those 5 subsets, and one of them is kept aside to use for evaluation, kind of like a mini test data. And it does that for each of the folds. And so the model is really being trained 5 different times. And then what it does is it takes the performance from each of these 5 trainings and averages across all of those. So it takes the average performance across all of these folds. And that is how it decides what is the best setting of hyperparameters. So this is really, this technique, approach, method, whatever you want to call it, is really useful in hyperparameter optimization because you're selecting the set of hyperparameters which have the best performance on a variety of data, and it reduces the chance that you're overtraining or overfitting your model. So just a quick word on overtraining and overfitting here. Overfitting or overtraining is something you constantly be cognizant of in the model. And the gist of it is, when we split our data into the training and test sets, the training set, of course, is finitely pretty limited in terms of statistics, like rows, number of examples. So because this training data is very finite, we always run the risk that there arises some statistical anomalies, spurious correlations, etc., that come up in our training set just purely out of random chance, that only exists on our training set because it's just a random fluctuation. And when we go back into the real world, we'll see that there really is no those correlations, whatever relationships, don't really exist outside of the training set. And so that can be a problem. And so when these statistical anomalies happen to pop up in our training set, it can create a headache for us, especially when we're using very complex, very sophisticated models that have the ability to learn a lot about that training set. And so they can really start to pick up and learn about these spurious, anomalous correlations. And so when you have a really sophisticated model, it can learn stuff really quickly and easily. And the problem is, that's not the stuff that it learned that just happens to be in that training set isn't actually true. And this becomes a bigger and bigger concern the more complex our model is, and the greater risk we have that it learns these anomalies. And of course, the performance is going to be worse. And so this is what's known as overfitting or overtraining. And cross-validation really helps to solve this problem by splitting it out all these different ways, because the chances of a random correlation existing in each of these folds is much smaller. So that's really the idea. So there's a constant kind of trade-off or tug of war between having a really complex model that learns a lot and quickly, and guarding against overtraining. And so that's kind of the tug of war between model complexity and fighting against overtraining. And so I'll just link you to this bias variance trade-off. That's kind of what we're wrestling with here. But we're going to use grid search CV, this function in Scikit-learn, to address this problem. So grid search CV looks like this. So we specify our model, which is f prime, which is our support vector machine, and we're going to specify this thing called param grid. This is all the different hyperparameters we want to try. So for C, I want to try 2 different values of C. I want to try 100,000 and I think it's 1,000,000 here. For kernel, I only want to try 1, which is RBF. To score it, we're going to use the same scoring we've stuck with before, which is the mean squared error. So that's how it decides which one is best. The cross-validation, the CV value, that is just the number of folds. Here I've chosen 2, which is actually a pretty small, a really small number. We've set it to be verbose so we can see the status of things as we're training. And this is just the number of processors that this grid search will run on. So I'm gonna go ahead and we'll fit it. We'll run the fit function just like it were its own model. So I'm gonna run the cell, and this is gonna take a minute. And so what it's doing now is it's scanning over this grid of possible values. So it's training the model. So we've got 2 different unique sets of hyperparameter combinations here, and we've got 2 different folds in our cross-validation. So 2 times 2 is 4. So there's going to be, we're fitting the model 4 separate times, and we're asking, which one had the best set of hyperparameters. So I really strongly recommend you pick a larger value for your CV. I would suggest like at an absolute minimum of like 3 or 4. But the reason I'm picking such a small number here is because this grid search can take up a lot of memory and CPU on your computer, and you can easily crash your machine. So I have this statement in the comments: be sure not to make this grid too big. So, as we saw before, there's lots of hyperparameters we can pick, and we could put in, like a dozen more values for C here. But to make this to be able to like present this to you guys in a reasonable amount of time, I had to pick, I just had to scan a really small number of hyperparameters, but we could really add all these other hyperparameters and put in a range of values for those. And our grid search would, try each one of those for each of the folds. And so it can really take a long time. So I do caution you to be careful about that, and patient as well. Okay. Now the fan on my laptop is definitely, I can hear it. It's definitely pretty loud now. So I know it's working hard, plugging away. So let me just skip forward now for a minute. So one of the things we can call is we're going to grab our CV results. So basically, it's the results of our fit that we ran up here, our cross-validation and grid search, and we're gonna convert that to a Pandas data frame because this object here is really a dictionary. So we're going to convert that from a dictionary to a Pandas data frame, and then we're just going to print that out. And we can see for each of our model runs or each of our model trainings, which set or combination of hyperparameters did the best. So I'll go ahead and hold Shift and push Enter for that, and we can see which one was the best. While we're still waiting for this, I'll cover what's going on in here. So we're going to redefine f prime as this thing called best estimator, which just returns the best model from the results of our grid search. So, okay, cool, we're done training. So this is kind of a result of our training, and you can see the different hyperparameter settings here. You can imagine if we had done more than 2, we would have, that's going to be, we'd have way more rows in this data frame. But we can see the mean test score. And what you'll notice, so this is our mean squared error for that particular test and fold. And what you'll see is that, they're kind of big. And not necessarily better. But remember that the data this is being run on are just subsets or folds of our training data. It's not the same data we were calling back here, which is our testing data. So that's important to remember. And so we're going to grab the best, whichever one had the lowest MSE from this set, and set it equal to f prime, which is our model. And then we're going to call the predict, and then we're going to get the mean squared error from that. And then what we get out from this cell is actually going to be an apples to apples comparison. So what you can see now is that our mean squared error went down by quite a bit. Now we've got a mean squared error of 97.5 compared to up here of 101, basically 102. So we had a pretty good improvement there by picking the right values of our C parameter. So that's just a really cursory example. There's way more things we could optimize. I am in no way guaranteeing that this is the best set of hyperparameters, but we can see, I think this is useful in demonstrating how we can improve, or how we did improve. So let's kind of visualize things here. And what we're going to do is we're going to plot our predicted values versus the actual values as a function of flight duration. Now, remember, the model is learning more than just flight duration. It's giving flight duration as well as departure date time. But for now, we'll just visualize it as flight duration. So we'll click, hold Shift, and push Enter. So you can see here, this is how the support vector machine in this plot is thinking about our data. So again, the blue is the prediction that our support vector machine model gave us after running the cross-validation and optimizing the hyperparameters. And the red is the actual data. So we're doing, you can see there's a nice spread here. So to compare or contrast this to the linear model, if we had stuck with that linear model, all we would see is a straight line of blue points. So you can see the added complexity that the support vector machine really gives us, and that's really borne out in the mean squared error as well. So I'd say that kind of gives you an overview. Again, this was my goals here were definitely not to teach you about how support vector machines work, but I really wanted to get you familiar with kind of the machinery and how you can implement it. And I think there's tons of great YouTube videos, some that I've linked in the cells above, that you can use to really understand what's going on in those models and what those hyperparameter knobs and dials are really adjusting as you're changing them. But here, you can see that with grid search and cross-validation, we really can do a better job of estimating. So that's what we covered today. Definitely thanks a lot for your attention. Next time I'm going to try and have the next session as soon as possible. We're going to go over how to compare multiple models kind of in one go, and there's a link to get you started on that. One important thing is one-hot encoding of categorical features. So what I mean by that is, if we go back to our data frame here really quickly, you'll see that we had some things like month, weekday, stuff like that are strings. And not every model can just take a string and know what to do with that. And so one-hot encoding allows us to basically pass strings to our model is a way of thinking about it. So we'll cover how to do one-hot encoding, and then we'll start to talk about classification and hopefully clustering examples as well. So I'll just say, yeah, thanks, definitely thanks. In closing, I would have loved to show you some COVID-19 modeling and stuff like that, but I think it's either too pedestrian for this audience or probably too complicated without the modeling background. But if you have any questions or interest in doing some COVID stuff or have some COVID data, please share it in the Python group, and we can talk about it and go from there. So I know we're pretty much out of time, so thanks again. And if there's any questions, I'll just stay connected to this meeting to answer those questions. Let's see, I can't hear anybody. Did I make a mistake? If anybody's talking.
Hear me?
Hey, Mike, I can hear you. Yeah.
Just thank you for doing this. I didn't realize you'd offered this already, and so I'm one behind, so I'll have to go back. But I'd used Anaconda for some flight data for the, used to be 4G projects, now it's going to be 5G project.
Awesome.
So, but I would say I'm not a super user by any means. We were kind of playing around with MATLAB and with Python and seeing which way worked best. Also interested in the COVID stuff, but we'll see whether we stay caught up. But thanks for taking care of this.
Yeah, thanks, Mike. Thanks for the feedback. Really appreciate it. Any other questions I can ask, or maybe make more clear? Any things I can make more clear?
So I assume I just download the previous week's package the same way?
Yeah. Yep, exactly. And there's a recording of that session posted to YouTube that you can follow along there.
Load the notebooks and make sure everything runs.
Yep, exactly. And ping me if you have any snags in that process. Yeah.
All right. Thanks.
Yeah. Thank you. Okay, well, thanks everybody for connecting. If there's no more questions, I'm going to stop recording and close the meeting. But I'm always available via email and Slack, so happy to answer some of those questions there. But yeah, I just wanted to thank everybody for coming again, and I always welcome suggestions, feedback, improvements, etc. So thanks again, everybody. Appreciate it, and have a good rest of your day.